everyone, this is Shruti. Welcome to our channel Shiv Rising Star. This is our 10th lecture on electromagnetic theory. In this lecture, we are studying about the applications of Gauss law. So let's start the applications of Gauss law. Application of Gauss law. Gauss law is valid for any distribution of charges and for any closed surface. So, Gauss law can be applied in two ways. First one is if we know the charge distribution, then we can find the electric field. Second one is if we know the electric field, we can find the charge distribution. So, when we know the charge distribution, we can find the electric field by using Gauss law. And when we know the electric field, we can find the charge distribution by knowing the Gauss law. Electric field due to uniformly charged spherical shell. So we have a spherical shell and we have to find the electric field at outside the spherical shell, inside the spherical shell and on the surface of spherical shell. So by using Gauss law we can find the electric field outside the spherical shell, on the surface of spherical shell and inside the spherical shell. So we have to apply the Gauss law here. So we will do the Gaussian surface here. So this is the one Gaussian surface. Okay. So we consider the one point P on this Gaussian surface. So this is the point P on this Gaussian surface. And we take the small area of this Gaussian surface. We consider it is a dA and we have to find the flux of this small area. The flux of this small area dA is d phi E is equal to E bar dot dA bar. So electric flux is the multiplication of electric field into area. So this is the flux of this small area dA. If we integrate this flux, what we will get? Integration of d phi E is equal to integration E bar. This is the closed integral. So Gaussian surface is the closed surface. So this is the closed integral d phi E is equal to E bar dot dA bar. So integral of this is phi E is equal to this E electric field is a constant everywhere. That is electric field uniformly charged spherical shell. So electric field is uniform everywhere. So this is outside the integral E bar and the closed integral of dA bar. dA bar is the small area. And when we integrate this small area, we will get the whole area, that is A bar. It is phi E is equal to E bar dot A bar. And this is the dot product. And how we will open this dot product? It is phi E is equal to E A cos theta. So we can write it as phi is equal to E A cos theta. And here the direction of the electric field is in this direction and the area vector is always normal to the surface. So this is the surface and the area vector is always normal to this surface. So both are in same direction. Electric field and area vector both are in the same direction. So angle between them theta is 0 degree. And we know that the cos 0 is 1. So we put this theta is 0 and cos 0 is 1. So we can write it as phi E is equal to E into A. And this A is the area, but this A is the area of spherical shell because this is we take spherical shell. So what is the area of sphere? Area of sphere is 4 pi r square. Gauss law, that is phi is equal to Q by epsilon naught, or this is phi, this is phi. So left hand side of this both, suppose this is 1 and this is 2, this is according to Gauss law. So this is 1 and this is 2, left hand side both are same. So this is phi. So we can equate this right hand term. So we can write it as Q by epsilon naught is equal to E into 4 pi r square. Okay. And we know that the sigma, surface charge density, sigma is equal to Q by A. And when we have to find this Q value, Q is equal to sigma into A. Okay, and Q is equal to sigma. A is the area of the sphere. So here area of this sphere is 4 pi and the radius of the sphere is r square. Okay. Here we take small r because this is the distance of this point from the centers. We have taken this Gaussian surface distance, and this is the r, this capital R is the radius of the sphere and the small r is the radius of the Gaussian surface. So here we take radius of the Gaussian surface and here we take the radius of the spherical shell. So Q is equal to sigma 4 pi r square. So we will get the value of Q. So we can put this value in this equation. So what is this? Sigma 4 pi r square by epsilon naught is equal to E 4 pi r square. So here we have to find the value of E. So we can write E is equal to sigma 4 pi r square upon epsilon naught 4 pi r square. So here 4 pi is common. So it is cancel sigma r square upon epsilon naught. This is small r square. So this is electric field at outside the spherical shell. This is the electric field at outside. And on the surface, suppose on the surface, suppose on this surface, and at that time the small r becomes capital R, okay, because radius changes on the surface. Everything is same but radius it changes, and on the surface r is equal to r. So we can write it as, instead of this r we can take capital R. So E is equal to sigma r square upon epsilon naught capital R square. So this r square get cancelled. E is equal to, on the surface, is equal to sigma by epsilon naught. And inside this sphere, okay, inside the sphere, okay, inside this sphere there is no any charge because the charge is reside on the surface. Okay, charge is reside on the conductor. Okay, so inside the conductor there is no charge. So in this case Q is 0. So when Q is 0, then electric field E is 0. Okay, if there is no any charge, so there is no any electric field. So on the surface is sigma by epsilon naught outside the spherical shell, that is sigma r square upon epsilon naught r square, and inside the spherical shell the electric field is 0. Question is that find the electric field due to uniformly charged solid cylinder. That is, we have to find the electric field outside the cylinder, on the surface of cylinder, and inside the cylinder. So we have a solid cylinder and the radius of this cylinder is r and the length of the cylinder is L. We know that the area of the cylinder is 2 pi r L and the volume of the cylinder is pi r square L. We have to find the electric field outside this cylinder. So we take the point P, which is outside this cylinder, and we have to calculate the electric field at this point. For that we have to draw the Gaussian surface. So we draw the Gaussian surface here. So we have to draw the Gaussian surface, and we have to find the electric field at this point P. So this is the radius of the cylinder and the distance of this point from the center of the cylinder. So we will take small r. Okay, and applying the Gauss law, we can calculate the electric field at this point. So we know that integral E bar dot ds bar is equal to q by epsilon naught, and this is the uniformly charged, so electric field is the constant here, so we will take it outside, and integration of the ds, this is the small area, so integration of this is total area s, so this is es is equal to q by epsilon naught. But we know that the volume charge density rho is equal to q by v enclosed. Q enclosed, v enclosed. So we have to find q. Q is equal to rho into v. So V is the volume. So and volume of the cylinder is rho into pi r square L. So volume of this cylinder is rho into pi r square L. And S is the area, and this S is the area of this Gaussian surface. So E into area of the Gaussian surface, we know the formula for the area of the cylinder is 2 pi RL. Here R is the small r, so this is 2 pi RL is equal to, what is the value of Q? Q is rho pi r square L by epsilon naught. So E is equal to rho pi r square L by 2 pi r L epsilon naught. So what is the common here? Pi, this pi get cancelled, L get cancelled. So what is remaining? Rho r square 2 epsilon naught r. So this is the electric field outside the cylinder. And when the electric field on the surface of the cylinder, on the surface. So what is the value of this R? This R becomes this capital R. So R is equal to capital R. So here we can write this is E on the surface is rho R square and 2 epsilon naught R. So this R becomes this R. So we can write it as R. So it is rho R, 1 R get cancelled, rho R upon 2 by 2 into epsilon naught. So this is the on the surface. So this is the electric field on the surface. This is the electric field outside the surface. Inside the surface, so we consider the electric field. We have to calculate inside the cylinder. So we consider this is the R, and inside the cylinder, that is inside the cylinder. So we know that integral E bar or ds bar is equal to Q by epsilon naught. This is the constant E. Integration of this ds is S. We know the value of Q is rho pi R square L by epsilon naught, and this is the area of the this. So this is the area of this is E is 2 pi R L. So rho pi R square L by epsilon naught. We have to find the E. So E is equal to this rho pi R square L by epsilon naught into 2 pi R L. So this pi get cancelled, 1 R is get cancelled, L get cancelled. So this becomes E is equal to rho R by 2 into epsilon. This is the electric field inside the cylinder. So outside the cylinder, electric field outside the cylinder is rho R square upon 2 epsilon naught R. On the surface, it is rho R by 2 epsilon naught, and inside the surface E is equal to rho R by